Hello, students. This is Mr. Allen, and I'm going to look at sections 4.2 and 4.3 with you today. I am going to use my smartboard today to do this. There's just going to be a lot of writing, and it's just going to be a lot easier for me to use the smartboard. So without further ado, we're going to go ahead and get started, and I am going to try to limit this to about 15-minute presentation. So we want to look at something called sigma notation today. We want to be able to approximate area plane regions, and I'm actually going to find some exact areas. And then we want to utilize properties of definite integrals. So first thing I'd like you to be aware of is this is sigma notation. So sigma is the word that we use for this symbol right here, this kind of E looking thing. And it's just a way of writing repeated addition. So if I want to add up a bunch of things, I can write it more compactly using this. And this I is the index of summation, so that's why we call it I. And then the upper and lower bounds of the summation in this case are 1 and n. So here's an example of a sigma notation. So you may have seen this in pre-calc or algebra 2. So if I want to add the first 6 natural numbers, so I would just put 1 in and then 2, which is the next number, and then 3, and then it means to add all of those up, and then we could figure out what that sum is. In this case, that's pretty easy to do. So that's going to be 7 plus 7 plus 7. So this is 21. We can make it a little bit more complicated expression. So this one looks a little bit different than the first one. But what's interesting is once you start plugging the 0, 1, 2, all the way up to 5 in, you end up getting the exact same sum as that we mentioned before. So that's, even though these look different, these are equivalent sums. And of course, we could have squared things. We could even have square roots. It could be basically any rule that you want to make up. We could even put k squared and then put an n there. So in this case, this expression is variable. Notice that each one of these has a n term in them. So this is, it doesn't have to come out to be one specific value. And then this one here, this is going to be very helpful. We're going to use that today when we talk about definite integrals. So it can be a very complicated looking expression. Okay, there's a couple of properties you need to know about sigma notation. Number one, there is the constant multiplier or scalar multiplier, which basically says if you have got a sum of some number like k times some variable expression, you can just pull the k out to the front. So we've seen that property before in some of our other things like limits and derivatives. And then there's also a formula or a rule for the sum or difference of things. So if you're doing the summation of a plus or minus bi, then that's simply going to be the sum of a plus or minus the sum of bi. So again, these two properties follow from things that we've done in the past, and I think they're fairly intuitive. Now, I'm going to put a star next to this one because these are our summation formulas that are going to be required for us to do some of the harder problems of this semester. And basically what these rules are saying is if you have the sum of a constant, like so if I have this sum from I equals 1 to, let's say, n of, let's say, 7, this rule tells us the answer is 7n, and that's basically it. So if I had the sum of I equals 1 to, let's say, 3 of 7, well, that's 7 plus 7 plus 7, which is 21, which is, oh yeah, it's 7 times 3. That one's, no one's going to argue that, I don't think. But here are some more interesting ones. So we will use this one a lot. So if I want to sum the i's, so those are the i's, the formula turns out to be n times the quantity n plus 1 over 2. And then there's one for n squared, and then n to the third. And I'm just going to let you know right now, in general in this class, I probably would not expect you to ever use that one. This would be the worst case scenario. Typically, it's going to be 1 or 2. So here's an example. I'm trying to find the sum of this for n equals 10, 100, 1,000, and then up to 10,000. So the first thing that I could do is I could just do this manually, right? So in other words, I could say, all right, so let's let n equal 10 here, okay? So then that's going to be the sum of I equals 1 to 10 of I plus 1 over, and remember, n here is 10, so this is going to be 100 on the bottom. So that's going to be, well, we got to start with the first one. So that's 1 plus 1 over 100 plus then 2 plus 1 over 100 because now I has now incremented up 1 plus 3 plus 1 over 100 plus da 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 all the way up to the 10th one. And then when we sum all of those up, it turns out to be 0.65, which we could calculate, be kind of a pain. The good news is you got a common denominator, so when you add up all the numerators, you get 65. The problem is are we going to want to do this with 100, 1,000, and 10,000? And the answer is, well, probably not. So the second option we have is we have our graphing calculators. The second option we have is we have our graphing calculator, particularly if you have one of the nicer graphing calculators. If you go to Math 10 or 0, you will see that there is actually a summation formula in there that we could literally type this in. I'll do that now. I'll say x equals 1 to 10. Now I'm using x here instead of I. And then it's going to be x, let's do some parentheses, x plus 1 divided by 100. And I hit enter, and it gets the 0.65. The third option that we have, though, so we could use a calculator. The third option we could do is actually do an analytic approach. In other words, what I could say is I could use those formulas on this previous slide. In particular, I'm going to use this guy. And when I use those formulas, I'm going to get the following. So this sum, which is I from 1 to n of I plus 1 over n squared, well, that's the same thing. Now notice that this summation only has to do with the variable I. So what I can do is I can actually pull out that 1 over n squared. In fact, I'm just going to go ahead and do that. Since this does not change, it is constant throughout whatever, once we establish what n is, it does not affect it. So this is one of those properties I mentioned earlier. So this becomes I plus 1. We're still going from 1 to n. And this needs to be in parentheses because I'm doing the sum of this. So this is now 1 over n squared, and then it's the sum of I from 1 to n plus the sum of 1. And this again is from I equaling 1 to n. So now I'm doing this. And now we can use our formulas from this slide. Namely, I'm going to use this formula and this formula. So this is going to give us the following. 1 over n squared, that's this. And what is this here? Well, that's n times n plus 1 over 2. And then plus, now I've got to do the distributive property here. So this is going to be 1 over n squared times, and now what's the sum of 1? Well, the sum of 1 based on this formula is just going to be 1n, or I'll just say that that's n. And now what we can do is we can go ahead and work this out algebraically, and it turns out that the answer is, in fact, I'll imply that there's some work shown here, but you're going to have a nice common denominator and work all these things out. You're going to n plus 3 over n times 2. So this is equivalent to this, So now we can even check that. If we plug 10 into there, well, that's going to be 10 plus 3 over 2 times 10. So that's 13 over 20, which turns out to be 0.65. In other words, I don't have to add all those things up. And we can see all of the work here in this following table. So this is the one that I did manually. Here's our formula again that I derived using these rules on the previous slide. And then, so if you do it for 100, you'll get this. If you do it for 1,000, you get this. And if you do it for 10,000, you get this. Now, here's a question, and this is an important question. As I keep adding values to this thing, as I keep increasing the number of things that I'm adding, the number seems to be getting smaller and smaller. It almost seems to be approaching a limiting value of some sort. I wonder if n was infinity, what this number might be. Okay, let's go ahead and move on. All right, so The next example we're going to look at is now I want to approximate an area. So I'm going to kind of move a little bit away from the sigma notation for just a second. And I'm going to focus on two things. So I've got this function here, and I want to approximate the area under that curve, okay? So this curve, you guys are probably familiar with it. It is a parabola that does something like this. And I'm trying to approximate it between x equals 0 and x equals 4. So we're talking about from 0 to 4 here. So we've got 1, 2, 3, and then 4 here. So that'd be 1, 2, 3, and then 4. And I want to basically kind of figure out what the area is underneath that curve above the x-axis. So we can do this two ways. Actually, there's more than two ways, but in this example, we're going to just approximate it from the left. So what I'm going to do is I'm going to use something called like a Riemann sum or a Riemann rectangle. And Riemann's just the name of a mathematician. So what we're going to do is we're going to draw some rectangles here. So in order to draw this rectangle, we probably also need to know the following. If x is 0, then x squared is 0. If x is 1, then 1 squared is 1. 2, 3, 4. So that'd be what? 4, 9, and 16. So I've got all of these. So if I'm measuring on the left end of this, so what that means is I'm going to measure here, and I'm going to have a rectangle. Then at 1, I'm going to measure, and by the way, that would be 1, so that would be a rectangle. And then at 2, this would be a rectangle. And then at 3, it would be this rectangle here. And so I'm going to have 1, 2, 3, 4 rectangles to approximate this area. So this area is, in fact, I should probably use approximately. Let me change that to approximately. So this area is approximately from the left endpoints is going to be each width is 1, but the heights then are determined by these values here. Now, since it's a left endpoint, that means I'm going to measure on the left. So measure on the left. So when I measure on the left, I'm going to get 1 times the height there, which is 0, plus the second rectangle is going to have a base of 1. And what's its height going to be? Well, it's going to be 1 plus. Then the next rectangle is going to have a width of 1. And what's its height going to be? It's going to be 4. And then the next one's going to have a width of 1 and a height of 9. And when we add all of these up, we get the answer of, well, 0 plus 1 plus 4. So I think that's 14. So this is an approximate area for underneath that curve. Now, just to let you know, if we did this on the right endpoints, let's do that in red, the right endpoints. So we're going to measure on, instead of the left, we're going to measure them on the right. Now this area is going to be approximately 1 times, now we're measuring on the right. So that means we're going to start here, measure this way. That's the first rectangle. We're going to measure here, that rectangle, here, that rectangle, and then here, that's that rectangle. Now we're measuring on the right-hand side, so that's why I'm coming from the right. So that's going to be 1 times the first height, which from the right is this one, so that's 1, plus 1 times 4, that's the second one, plus 1 times 9, that's the third one, and then plus 1 times, and the last one would be 16. And that turns out to be an answer of 30. By the way, this is what we would call an under approximation. This one is over approximation. So the question I have is, where do you think the exact answer is for that area? Okay, so we're going to go ahead and move on. This is a very important slide here. This is probably in terms of finding the exact area under the curve. And guys, I'm looking at my time here and I can tell we're not going to be at 15 minutes. So I guess hopefully I'll get it under 20. So this is our formula for the area under a curve, exactly, basically. And we're going to have to use this thing called a limit, which we've talked about before. And the limit of the sum of the value of the function at some x value called c sub I, and then some delta x. And delta x, this is just the width of each rectangle, which is what we kind of looked at on the last example. And by the way, here's the formula for delta x. So let me just kind of give you an example of, or let me work one of these out to show you what that is. So this area is equal to the limit as n goes to infinity of the sum of I equaling 1 to n of f of c sub I times delta x. That's our formula. This is the first thing you want to write down. And now let's go ahead and figure out what some of these things are. So first of all, delta x, the formula is b minus a all over n. Well, in this case, here's A, here's B, so that's going to be 3 over n. C sub I, there's a formula for that. In this case, since we're starting at 0, it's just going to be 3 over n I. So that I, we're just going to tack an I on there. So you just kind of got to trust me here. So this formula then becomes the limit as n goes to infinity, sum of I equals 1 to n of f of, instead of C sub I here, I'm going to put 3 over n I, and then we're going to multiply that by delta x, which is 3 over n. So there's our formula. And let's go ahead and clean that up a little bit here by substituting what we know. And in this case here, f of x is right here. So this is going to become 2 times 3 over ni. So I'm plugging that in for our x, then plus 5, and then 3 over n. And now I'm going to keep playing this game and trying to simplify this and figure out what this is using our formulas, okay? So this is going to give us the following: the limit as n goes to infinity. And I'm not going to write all this sum stuff out. So I'm going to multiply here. This is going to be 6 over ni plus 5. And then I've got this 3 over n here. Now I'm going to go and distribute. So that's going to give me this sum of, and that'd be what, 18 over n squared I plus 15 over n, like so. And now at this point, I'm going to start pulling things out and using some of those properties that I've mentioned earlier. So this first thing is going to be 18 over n squared times the sum of I. So this 18 over n squared doesn't have any I, so I'm going to do the sum of I. Plus, and then I'm going to have 15 over n, and then the sum of 1. And now I'm going to go back and use those formulas that I've mentioned, and let me highlight those. So I'm talking about the formula for this and the formula for this. And so that's going to give me the following. So that's going to give me the limit as n goes to infinity. And this is going to be 18 over n squared, and I'll do this in red. So that's going to be n times n plus 1 over 2. That's the first substitution. There's a times right there. And then this second guy is going to be plus 15 over n. And I'm going to substitute what this is, and this is just going to be times n. And there we go. So everything's looking okay. I'm actually going to kind of come up here and finish this guy off. Now, I claim I've already kind of worked this out in advance to speed this process up. But basically what you're going to get is the following. You're going to get the limit as n goes to infinity of 18 over n squared plus n, oops, not plus, this is times, 18 times n squared plus n over 2 plus, and then 15 over n times n. And so these n's are going to cancel, and you're left with just 15. So this is the limit as n goes to infinity of, and now this n squared is going to cancel that. That's going to become 9 plus, and then this is going to be 9 over n plus, and then those are going to cancel. That's going to give you 15. So I tell you that the exact area under this curve is exactly 24. Exactly 24. All right, so here's some more about the definition of the Riemann sum, which I will leave that for you to read. Here's our definition of a definite integral, and this is also important. This right here, and I'm just going to point this out right here. This right here is synonymous for saying that n goes to infinity. So this is that formula that we just saw. This is what we call the definite integral. The definite integral. So the definite integral is equivalent basically to what I just did. All right. Here's a theorem that basically says that continuity implies integrability. In other words, if it's continuous, you can integrate it. So if we wanted to evaluate this, the way that we're going to evaluate it is we're just going to use the formula that I just talked about, n goes to infinity, summation of I equals 1 to n of, in this case, it's going to be f of c sub I delta x. That's what we're going to do, except now this is the f of x. This right here, this is where we're going to start. So this is our a. This is where we're going to end. So that's our b. So this integral is going to be the following. The limit as n goes to infinity, summation of I equaling 1 to n of 2 times. And now we've got to plug in our x sub I here. And our x sub I here is not the same thing that it was earlier. It's a little bit different because we're not starting at 0. This is actually going to be negative 2 plus 3i over n. And then all of this is going to be multiplied by 3 over n. The interval is still 3. The length of the interval is still 3. Now I'm just going to let you know that this answer here turns out to be negative 3 if we go through the same process I did earlier, which does not seem to be too intuitive. But it turns out that when we were talking about this curve, y equals 2x, that's this curve right here. This curve right here. And it turns out that if we're going from negative 2 up to 1, this area is positive, and it turns out that this area, since it's below the x-axis, is considered negative. It's considered negative. All right, here's a couple of special definitions. It turns out, number one, that the integral from a to a is 0. The integral, if we switch the a and the b around, it becomes a negative. I would highly recommend that you know those. There's also, we can break it up. We can break it into consecutive addition. So if I'm going from a to b and I know that c is between a and b, I can break it into 2 separate parts. And then last but not least, we can see that we've got some properties. There's that constant multiplier property again and the sum and difference one. So guys, I know I'm running long here, but this is the last example here. So I'm going to use all those properties on the previous 2 slides to answer this final question. So I can rewrite this integral as follows. I can say it is the integral from 1 to 3, and I can pull the negative in front and leave this x squared dx. And then plus, and this is by the sum and difference part. So now I've got to do this next part here. So that's a 4. So 4 can go to the front. And again, I'm going to go from 1 to 3, and that leaves me with just x. And last but not least, this negative 3 can go to the front. And then I'm going to just integrate from 1 to 3 of dx. So I'm using all of those properties that we just talked about. And in this particular case, we know what the integral of x squared is. This is going to be 26 over 3. We know what the integral of x is. That's going to be 4. And we know what this last integral is. This last integral is going to be 2. So our final answer is going to be negative 26 over 3 plus 4 times 4, because of the 4 times 4, and then minus 3 times 2. And then we can work that out. In fact, I'll do that very quickly here with my calculator just to make sure I don't make any careless mistakes. Minus 26 divided by 3, and I get 4/3. So the value of this integral is 4/3, and we're going to stop there.